good afternoon, everyone, and good morning to some of you after the coffee break. I hope the coffee was good. And our next speaker is Martin Bojowald from Penn State University, and he's gonna speak about physical implications of a fundamental period of time. So Martin, thanks you for joining us, and the teams are yours.
Okay, thank you for the invitation. I'll talk about mainly two papers, a pretty old one, which was initially a formal and conceptual discussion of the problem of time with Marcelo Amaral. And just recently, well, not 3 years, but recently we finalized this. It was hard to see what was going on in the old paper, so Garrett Wendell, in particular, as an undergrad student, started doing numerics and discovered several surprising features, which we just finished, and the preprint will probably appear tomorrow. We just got acceptance from the journal. So the second part will be more physical and maybe what's more surprising. But first, a review of the problem of time and some of the proposed solutions that we will use later. So the absence of an absolute time in general relativity means that dynamic equations are constraints. So in simple models, and that's basically all we'll be using in this talk, just a single degree of freedom for gravity. We have the Friedmann equation, which is first order, so that's not the typical evolution equation. It's rather a constraint, which we can see when it's rewritten in phase space. V and PV are the canonical coordinates related to the scale factor. And I just assume some scalar field which determines the energy density. So classically, of course, there's a dot here, so we know how A and phi depend on time if we can solve these equations. But when it's quantized, this C equal to 0, the phase space constraint is turned into a condition on the wave function, which just tells us that it has to be annihilated by the constraint operator. So it's not obvious how phi evolves at the quantum level. A possible solution is deparametrization. It goes back to some suggestion by Dirac in the paper a long time ago. And it's been used very often recently, in particular in quantum cosmology, even though it's not very realistic because it requires a very special matter ingredient which can play the role of time. So this, the main example in recent applications is a free scalar. So just this energy density here, no self-interaction potential. So that's already pretty special. And then it's restricted even more by assuming that the mass also vanishes. So the energy density of the matter Hamiltonian does not depend on phi, it only depends on p phi. So the C we had from the previous slide now looks like this, and now it can be solved easily for p phi. Take a square root, do the other things. And if that's quantized, p phi is h power I d over d phi. So acting on a wave function up to a minus sign, this looks just like the left-hand side of the typical Schrödinger equation. And on the right-hand side, we can just come up with some quantization of VPV. And we get some kind of evolution equation if phi is now our time variable. In this sense, one can make sense of constrained evolution, but it's not realistic as a fundamental definition because it requires a field that has no mass, no self-interactions, but still contributes to the evolution of the universe because its kinetic energy appears in the Friedmann equation. So it is physical, but very special. At the quantum level, there are additional difficulties. On the previous slide, what I showed here is we first take the square root at the classical level and then quantize. Maybe more fundamentally, we would first quantize and then try to extract an evolution equation. That can also be done in the mathless case. We start with something like p phi squared minus h squared, some Hamiltonian h here. And this can be factorized exactly in two different ways if h does not depend on phi. So we have two factors, p phi minus h and p phi plus h. And they commute in the mathless case because h does not depend on p phi. So we could, if we solve the constraint equation, it could equally correspond to p phi equal to negative h or p phi equal to positive h. So we have these two branches. But that's no longer possible if the Hamiltonian does depend on phi. So in this sense, it's a time-dependent Hamiltonian. If phi is time dependence always makes things more complicated in quantum mechanics. And what happens here is we can factorize the initial p phi squared minus h squared, which came directly from the constraint. But we can't factorize this exactly anymore because there's now a commutator term if h depends on phi. And the commutator term, so that's the only thing that will be okay. A commutator is proportional to h bar, so it could be a quantum correction. But this term is different depending on the order in which we factorize the constraint. If we work with a single solution of the constraint, it can only correspond to one of the two, not both of them. It's impossible to have positive and negative p phi in a single quantum theory, even though if h is phi dependent, we normally classically would expect that phi oscillates. So it should go back and forth between positive and negative p phi. So deparameterization, which requires taking this square root here, is not compatible with the periodic clock, or any clock that is not just a monotonic function by construction. I'll present a few more formal details so from the first paper I mentioned, because that's what we'll use in the numerical and physical examples. But before we go there, it's useful to keep in mind a simple example. So I'm not using volume factors at this point, so I'll just assume a harmonic clock Hamiltonian with some frequency lambda and some system Hamiltonian h, which at some point in the numerics in particular will also be assumed harmonic oscillator. If lambda is equal to 0, we can just we obtain p phi equal to h plus minus h. So this would just be the standard quantum mechanics version of for the Hamiltonian h here. And if lambda is non-zero, we can see how we can describe a periodic time. Now what this looks like classically, if you work out Hamilton's equations with this constraint, the Hamiltonian h is conserved. So the constraint equation just implies that p phi and phi evolve on an ellipse in phase space. We will mainly consider large lambda, so large clock frequencies, short periods. So the idea will be trying to be close to something like a fundamental period given by the Planck time, for instance. So lambda, 1 over lambda should be very small, lambda should be large. So this means the ellipse is really very narrow in the phi direction. But again, just keep this, just some ellipse is a good picture for the next few slides. And this picture also shows that we need positive and negative p phi if we want to complete a full clock cycle in this classical picture. Full ellipse requires both kinds of p phi. As we just saw on the previous slide, that's difficult in deparameterization. On the next slide presents an independent argument, so that's more initially, at least, for the path integral perspective.
Marty, excuse me. There is a question. There is a question from Francesca.
Okay, I can see that. Yeah. Go ahead.
It's from Carlo, actually. Martin, why do you want a periodic clock? I mean, it's well known. There's a long discussion, Feynman, Edith, everybody, that no clock can be periodic. I mean, the things we call clocks are not periodic. That's the point about a clock, because you have to count things and so on. You want something non-periodic for having a clock.
Yeah, so you eventually you want some kind of effective time variable, which is not periodic. That's what we do by lining up minutes, hours, days, months, and so on. So that's clearly not periodic, but the fundamental process on which that is built is maybe not strictly periodic, but at least oscillating, because we need something to count. And if you have a strictly monotonic function, it is more difficult to count than counting periodic cycles. So I agree that the actual time variable or measurement that we extract is not periodic, but that's an effective degree of freedom, I would say. It's not a fundamental variable.
Right,
and,
but the thing we call time is not the oscillating variable, of course, it's something else. It might be built using an oscillating variable, but it's something that grows. Otherwise, it's not a time. It's not what we call time usually.
Yeah, so let's distinguish between time and clock. So the time variable we extract is not periodic. The clock is based on a fundamental process. And that's what I assume is going to be periodic, or again, not in a strict sense, just oscillating, just because it would be very contrived if we had to assume that there is a degree of freedom which does not have mass, does not have self-interaction, does not interact with anything else except for its kinetic energy. This looks to be very restricted, and there's nothing like this which we've seen in fundamental physics. So from a fundamental perspective, anything you can construct will at least have some turning points. Again, even if it's not strictly periodic, it will not be consistent with deparameterization, even if it has just a single turn. But we'll see how this non-periodic time emerges from this description here. It's actually on the slides here, the slide here. So phi will be the fundamental variable, and tau will be the global or non-periodic time variable. So let me just continue, for the next few slides with this more formal discussion, and then after that we'll see how we can make a transition from periodic clocks to non-periodic time. So again, formally, so that's an alternative explanation of why p phi cannot change sign, at least in the standard formalism. So if we choose phi as time, again, just some variable, some phase-space variable, that means we have to set it equal to a real parameter. So phase-space variable has to be set equal to a real parameter, which imposes a constraint, an additional constraint together with the constraint C, which would be the Hamiltonian constraint. And if it's a good time choice of phi minus tau, so as a constraint phi equal to tau, so phi minus tau equal to 0, should fix the evolution, the flow generated by the Hamiltonian constraint. So the Poisson bracket should be non-zero. And for the example that I just showed, so it would be a canonical example here, this Poisson bracket is equal to 2p phi. So that's non-zero as long as p phi is non-zero. And if lambda is equal to 0, so this would correspond to 0 mass, if it's really a scalar field, then p phi has 0 Poisson bracket with a constraint. The constraint is phi independent. So p phi is constant, and it stays non-zero as long as it is non-zero initially. So it's easy to maintain the gauge fixing condition. If lambda is not equal to 0, p phi is not constant, and generically it goes for 0 as phi oscillates. There might still be some cases for non-zero lambda. Well, not in this harmonic case, but in other models. But generically, whenever there's some phi dependence in the constraint, p phi changes sign. So that means p phi goes for 0. So in this condition up here, it's fixing phi minus tau is no longer a good gauge fixing condition. So then the language usually employed in path integrals, or gauge theories in general, p phi equal to 0 is a Greenberg horizon. So that's the place in phase space where a gauge fixing condition breaks down. So that's where we take some motivation from path integral quantization of gauge theories. The treatment there suggests that we should never cross Greenberg horizons. So in this case, crossing the horizons along paths that are included in the path integral. If we did that, we would overcount degrees of freedom, and we would not get the right result. So also here, since our Greenberg horizon is p phi equal to 0, we are not allowed to cross that. So we're not allowed to change the sign of p phi. And just as in the canonical description, that means it's not clear how an oscillating fundamental clock can be implemented. Our solution, with hindsight, as usual, is pretty simple. If we choose phi equal to tau as time, we are presupposing the direction in which phi moves with respect to this global time tau. Because we could equally choose phi equal to tau or phi equal to negative tau. And usually one considers only one option, and then the sign of p phi is fixed, and we can't get oscillations. But if we really want to describe an oscillating clock, we have to alternate different gauge fixing conditions. And once phi is equal to tau plus a constant, and then in the next half cycle, when phi starts going back on this ellipse, for instance, it should be equal to negative tau plus some other constant. And then the constants have to be adjusted to make everything continuous. The phi should still be a continuous function of tau. But with this description, we can use the global time tau. So in this case, this will really be a monotonic time variable. But it's constructed from an oscillating fundamental process described by phi here. This works, so we can now work out the Schrödinger equation with respect to tau, just using the chain rule. If phi over d tau is plus minus 1, this parameterization here. So even if h, the sign is fixed, so if we make a strict relationship between h and p phi, like our previous equation that did not allow us to change the sign of p phi, we have an extra sign factor here, p phi over d tau, which means that with respect to tau, we will have forward and backward evolution of phi, anything related to phi. So the periodic or oscillating fundamental degree of freedom can be described in terms of tau. An important condition is we have to make sure that this evolution is also unitary. So we'll do this on the next few slides. This one here first does not introduce tau yet. So in this case, evolution will not be unitary, but we'll see how this can easily be modified to include tau. Again, our canonical constraint here. Solve this for p phi, like this. So now with the phi-dependent expression on the right. And we quantize this. So this will be a phi derivative instead of p phi, and then some operator, depending on what h is. For the general discussion, I'll assume that instead of specifying h, I'll just assume we know the stationary state, eigenstates of h. So the Schrödinger equation in this k representation looks like this, can easily be solved with the space factor, this function. And the phase is real as long as phi is between its turning points, which depend on the energy. But for a fixed stationary state, that's just plus or minus ek over lambda. That's again the clock frequency. So there's a square root here and an arc sign. So if this condition, the inequality here is violated, the phase is no longer real, and so we don't have unitary evolution if we use phi as a global time, which is not surprising because classically phi has a bounded range. Now, introducing tau, so here that's a more explicit version of this piecewise linear parameterization. Phi equal to tau plus a constant or minus tau plus a constant, and then the specific constants are chosen for continuity. So this zigzag line here is just what we have in this parameterization. There's another parameter n here in the constants, which can be extracted from phi of tau, particularly in relation to the turning point values. And this, defined as an integer, it counts the number of clock cycles starting with n equal to 0 at tau equal to 0. This will play a role later on. When we start looking at small clock periods, we will have large numbers of cycles. But first, completing the proof of unitarity. So we go from phi to tau. We've seen that in the wave equations, the phase is replaced by d phi over d tau, the sign of d phi over d tau times the phase. It comes directly from the Schrödinger equation. And then phi is replaced by phi of tau. So the parameterization makes sure that phi always stays between its turning points. And then at each turning point, so whenever tau reaches, or we get to a maximum or a minimum here in terms of tau, we have to change the sign in the phase. So if you go through this cycle by cycle, or really half cycle by half cycle, because in each half cycle the sign is different, you can calculate the complete phase change per clock cycle. So clock cycle means we go from negative phi t to plus phi t and back. So that's going back as a factor of 2 here. And then we just take the phase values at phi t and negative phi t. And then with the previous expression, the square root is 0 at phi t, and we just get the arc sign. It's a simple value. So that's for each clock cycle. And then if you piece this together, so let's say tau might be many clock cycles after or before tau equal to 0, you get the first exponential, which is just the accumulated phase per clock cycle, or plus another half cycle if you are in the decreasing phase. And then plus or minus the phase that corresponds to the remaining piece if you haven't completely completed a cycle or half cycle. So this would be a solution of this tau equation. And as one can see here, these phases are always real. And theta k evaluated phi of tau is also real, because phi of tau by construction is always between the two turning points. So tau evolution is unitary for any value of tau. So in this sense, we have a global and monotonic time variable tau here, but it's not fundamental because it requires some constructions here to relate this to the actual fundamental variable phi. So that's the result for a single stationary state. And now, as usual, we can consider superpositions. The initial state determines coefficients, and then we just use the same coefficients in any tau. But as one can probably easily imagine, is as soon as you start going through turning points, the turning point values depend on Ek. So if you have different contributions from several stationary states, some of them start going through turning points earlier than others. So the phase relationships change and you start losing coherence. So that's where our numerics started, and you can see this easily here. So lambda is about 0.1. That's the clock frequency. So if tau is close to 10, the first energy values start going through turning points, and that's exactly the place where you see coherence getting lost. So the example here is a system Hamiltonian H, which is also a harmonic oscillator. So for lambda equal to 0, we know it should just be complete coherence. The state is also a coherent state initially, just some Gaussian. And we see that in the first maybe a little more than one system period. But then as soon as we start going through turning points of our clock variable, coherence is lost. as we decrease lambda, decrease this further, smaller and smaller, as we approach 0, the time where coherence is lost would move to the right. We would get a picture like this, which has complete coherence. That would not be surprising, but what's shown here is actually a huge value. So that's a situation in which we go through many clock cycles, even before, well before the first system cycle has been completed. Even the first branch here, we already go through lots and lots of clock cycles. So even in this large lambda range, so large clock frequencies, very tiny clock periods, we have complete coherence. There's only a few system cycles here, but you could just continue the numerics and you won't see any decoherence. So that was the first surprise. So if you have a very large clock frequency, even though you go through lots of turning points and you get lots of phase shifts, they all eventually line up just in the right way for the coherence of the system to be maintained. There's one difference here. If you compare these two diagrams, you notice that the frequency, the system frequency seems to be less. Everything moves, spreads out a little bit, even though we didn't change the system frequency. And this can actually be derived. That's an actual result which can be derived from the analytics. So here in this case, look at the coherent period. It's easy to believe that the period here in time is really equal to 2 pi, which should correspond to the values we chosen here, just system frequency equal to 1. In this case, the system period is closer to 8. And we can derive this. So we can also show why coherence is regained for large lambda. We assume large lambda for clock period. This means that the number of clock cycles at most time values is also large. And n over lambda can be well approximated. So that's the previous expression which I pointed out earlier for the number of clock cycles in our parameterization depending on tau. And lambda over ek are the turning point values of phi. If lambda is very large, can ignore the quarter here. The rounding it doesn't matter too much, so we can just approximate this as tau over ek. The same ratio appeared in the accumulated phase shift, which we used earlier to keep track of the total phase summed up over many cycles. So if we use the approximation for n over lambda, we get a phase shift which looks right. It's proportional to time. So that's the usual phase in the time-dependent wave function. It's proportional to the energy over h bar, but it has an extra factor of pi over 4 compared with just negative ek t over h bar. And that's exactly where this modified period comes from. So instead of 2 pi over omega, you divide this by pi over 4, you get 8 over omega. And that's exactly what we saw in the previous diagram. So that's an implication of the fundamental clock period, but it's not observable because we could just absorb this factor in the way we define the bare system frequency. And because this effect would be obtained, the same ratio would be obtained for any system Hamiltonian. It just depends on the clock system. We could just renormalize all the system frequencies and everything would be completely consistent with the two effect. Well, that's not an observable effect, but there's something observable in here, and that's the phase variance. So the dephasing, loss of coherence, is implied by the nonlinear phase, theta k of tau. So it's linear only at lambda equal to 0 or in the limit of very large lambda, lambda to infinity. Anything else, any finite non-zero value has nonlinear phase shift. And this means that different system cycles no longer have exactly the same period, even if it's a harmonic system. So there's an extra variance in the possible system periods that can be measured. And if you measure time very precisely, particularly in atomic clocks, which will be our next example, next slide, you can, you're sensitive to this variance. So to calculate this, so first define this as the usual way. So the actual phase minus the linear limit, and then square this and average it over cycle, or just a quarter cycle here, but then it's the same for a full cycle. Theta k had some square root and an arc sign, so it looks pretty complicated, but can actually be integrated exactly. And there's some numerical factors. Ek, 4 factors of Ek. Ek appears in the clock period, so that's 4 times the turning point value for Ek over lambda. And it also appears in the system period in terms of frequency. So if we combine these 4 Eks here with lambda squared and h bar squared, can write this as a relationship between the clock period Tc and the system period Ts. Factor of about 10 here from the numbers. And the important result is the variance is an extra factor. So if we want to probe very small clock periods, let's assume we want to get close to the Planck time, then the system period, we cannot do direct measurements on any scale close to the Planck time. But there's an extra factor of the variance here. If we do a very high precision measurement, even on a larger scale, system time, you can still could get an interesting upper bound on the possible clock period. Here first, diagram which shows the relationship. So the analytical approximation. I think that the labels are actually, they should be the opposite. So the right one is analytical, this straight line. So it would just be our the previous result, and then again, Garrett in the numerics has tested this numerically, and it gets more and more difficult to resolve this at very large frequencies, but it follows the linear. So now an actual example. So if we use the latest atomic clocks, use the values they provide, the precision is close to 10⁻⁹. So that would be our sigma, because this is directly related to the variance of clock periods contained in the measurement period. Sorry, the variance of the system. So the system here is the actual electromagnetic wave that used to set up the measurement. And then you wait for some time so you get many system cycles, MTS. And the precision is 10⁻⁹. So our sigma here cannot be larger than this value. The system period here is 2 femtoseconds, so that's a transition visible light, so not close to the Planck time. And if we use our previous equation, we get an upper bound on the clock period, which is about 10⁻33 seconds. Still 11 orders of magnitude above the Planck time, but it's certainly much closer than any direct measurement could achieve. And to put this in perspective, in particle accelerators at the highest energies, we can view them as distance measurements. You can measure a cross section with some precision. It's like doing a length measurement at the scale. The numbers now and in the foreseeable future is about 10⁻⁻20 meters, which is 15 orders of magnitude above the Planck length. So with this effect here, atomic clocks can actually beat particle accelerators in distance resolutions. The examples I showed here were mainly based on harmonic oscillators, and they're coupled through a constraint, so it's not just a harmonic oscillator system. But the main effect, which is this new dephasing, is actually model independent. It just requires a nonlinear phase. And that's always the case if we have a phi-dependent constraint, if we really have some fundamental field which has mass or self-interactions or any kind of interaction. A few suggestions for further development. So on a conceptual level, the fact that we regain coherence at very short clock periods justifies parameterization, because even though in this case we still use a fundamental oscillating clock, we don't have to assume that there is something monotonic. Parameterization is still a very good approximation, as long as the system period is not too close to the clock period. So this approximation should break down at the Planck scale. So if we're trying to do Planck scale physics, then we usually encounter system periods which are on the Planck scale, not just the clock period. And in this case, there can be significant effects from this dephasing or other implications of the fundamental description. So this might be relevant in particular in quantum cosmology. Quantum cosmology also requires additional technical development, because if the phi and p phi system comes from an actual scalar density, there are extra volume factors in the kinetic and potential energies. So if instead of just having h squared minus lambda squared phi squared, which is what I assumed in the main example here, you have an extra v squared, and h and v don't commute. So we cannot use this method of using stationary states of h. Or we can still use stationary states of h, but then v is not diagonal on this basis. So stationary states don't decouple the modes anymore, and it's going to be a much more complicated analysis, even numerically. And then finally, the upper bound is improved by, could be improved by using systems at high frequency or energy. So if we don't use atomic clocks, the frequency is not very large compared with high energy physics. But we also need the second factor from the accuracy. We need a precision measurement at high energy, and we don't have very many of those. But maybe there are other effects, cosmology or gravity, where we have long evolution times, which might eventually make us sensitive to this dephasing effect. We haven't really found any good example yet, but there might be. So that's where we are right now. So it's a pretty recent development, and we're still working on some of these other directions, and we're open to suggestions. Thank you for your attention.
Thank you, Martin. Let's thank the speaker. So we have plenty of time for questions. Any questions? Francesca and Carla, I see that your virtual hand is still raised. You want to still ask some question or not?
Not at this moment, thank you.
Okay. Someone else? So maybe from my side, Marty, you introduced that the periodicity through the scalar field. I mean, how this construction really depends on what kind of type of matter you introduce. Can you generalize it for some other type of matters, not only for the scalar field?
Yeah, so for the clock system, the main ingredient is so if you replace this the phi dependency with something else, you get a different equation for stationary states, which may or may not have an analytical solution. But it is going to be nonlinear. If there's any phi dependence on the right, you have the nonlinear dependence of the phase on phi or on tau, and you get the same dephasing effect, which we expressed here in this variance.
So you rather expect that the dephasing effect, I mean, due to the periodicity of time, is more general. It does not depend on the particular choice of the matter content, which is playing the role of the clock.
Yeah, it's pretty model independent. I think so. What we are assuming is that you have a clock Hamiltonian which is quadratic in p phi. So if you have a linear p phi, just like if you just done effective dust field for the parameterization, then you would not have this effect, because then if you have a linear kinetic energy, you don't get these oscillations. But again, this would not be fundamental as a relativistic. So anything that has a Hamiltonian quadratic in the momentum and some phi-dependent term would imply this effect. We haven't really checked yet how the numerical coefficient here would be affected by different clock times. So maybe there's a way to make the 9.7 smaller if you have a different clock Hamiltonian.
So
probably much smaller.
Mm-hmm. I think Sudo has some question.
Yeah, so you're saying that the dephasing effect, Martin, is it's not dependent on the potential, in the sense of if I have, you know, phi cube potential or phi fourth, if I have more interaction potentials, would that how would that affect the dephasing again?
I would not remove the effect. It would make it more difficult to solve this equation.
Sorry, it would make it what? It would
just make it more difficult to find analytical solutions.
But do you expect that it would be larger, right? If I have like more interacting potentials, self-interacting potentials?
You know what I would expect. But even if it makes it a little bit larger, I mean, it's mainly depends on the order of magnitude you have in sigma and ps. So I don't think a potential will help much in this upper bound on the fundamental.
Okay, so maybe derivative self-couplings, if it's not the potential, like it's not just the kinetic term, but derivative self-couplings, will that make it larger? Like I'm trying to say, the sigma looks like a very like a Gaussian effect. So how will I see non-Gaussianities in this effect, sort of something on these lines? So this theta solution that you have, how can this solution become such that, you know, it's strongly influenced by some self-interacting derivative couplings or something like self-derivative couplings and things like this? Is it, or is it very model independent in that sense? That's what you mean.
Well, if you have derivative couplings, you would probably change the momentum dependence as well.
Right.
Like, I don't really know what to expect in this case. I have to think about this. So yeah, model independent, I mean anything that is like a typical relativistic flat Hamiltonian. Yeah, that would require separate analysis. But the I mean, we've defined the variance here, but there might be, we haven't evaluated the skewness of this phase distribution.
Right.
So I'm not implying here that that's equal to 0. So even in this specific case here, even though the system and the clock Hamiltonians are both harmonic,
right.
I'm not really sure if the phase distribution is Gaussian.
So you mean in any theory, as long as it's not linear potential, there will always be this effect, which is obvious. But I mean, you don't know how strongly this will depend on. I mean, as you mentioned, like you haven't calculated like higher order moments here, like you just sigma square.
Right. No, it's
okay.
Yeah, pretty new results. So we haven't. There's still lots of things we.
Okay. Yeah. Thanks. Thank you.
Francesca, Carlo, you want to ask something?
Yeah, maybe I'm still confused about the conceptual ground of all that. The idea of the internal time and the clock time was not that in the absence of I mean, in a constraint theory, in a theory with relational temporal observable, you have some you have some oscillating thing, and you use this of time. It's exactly the opposite. It's known that if you want to call something time, you cannot. If you want to use a relational logic and pick an independent variables in terms of which you express the others, then you should not come back. I mean, this is so when in quantum cosmology, long time ago, the idea was, okay, so let's imagine there is a simple massless scalar field, and we can use that of time. The point was not we disregard its mass, and this is a fundamental object. The universe is full of all sorts of things, and among these all sorts of things, there are things which are monotonic in some approximation for a while. So we can have something which is monotonic and that happens to grow a fixed amount every time something else does an oscillation. But the time variable is a monotonic one, not the oscillating one. So it seemed to me if you want to study the physics of clocks, that's perfectly good, of course, and the physics of clock has quantum aspects. But let's not mix the fact that physical clocks are quantum with the fact that in general relativity you need, within some approximation, maybe for a while, to pick a monotonic variable as independent one in terms of which to do relational temporal observables.
Well, I don't see any contradiction with what I've been showing here, because tau is time and it is monotonic. And phi describes the clock, which is not assumed to be monotonic, but we're still able to extract an effective monotonic time variable from it. That's exactly what we do with our time measurement.
Right, but you don't have an independent tau variable, right?
No, it's not independent. That's in this sense it is relational, because tau is extracted from phi, from a physical parameter or a phase-space degree of freedom. But it is not itself a fundamental field.
The clocks are not fundamental fields.
Right. And
Why should they? Why should they?
Well, if there's some, I mean, if it is relational, then the assumption is that if we had a really full fundamental theory from gravity, then presumably that would become, well, it's a combination, maybe a collective combination of degrees of freedom, which play the role of a clock. I don't know what that would be, but it's from all we know about fundamental theories, it's unlikely that there's a combination which is completely massless and completely free of self-interaction.
Maybe we'll continue that in another place.
Any other question? So maybe just a continuation from my side. So concerning cosmology, application to cosmology, I mean, you can consider your phi as a clock, let's say, time variable, which is the periodic one in the model. But on the top of that, you need additional external tau parameter. Am I correct about that?
Well, it's not. It's not an external parameter in the sense that it couples to the other degree of freedom. It does not provide energy. So unlike the free massless scalar or dust field that one could use for exact deparameterization, these fields would modify, they have energy, so they would modify the expansion rate of the universe. This tau does not appear in the free quantum equation, so it does not provide any additional energy. It's It's external in the sense that it is not the phase-based degree of freedom initially. That's why it doesn't provide energy. So it's more like the time we actually extract. So if you provide a time and date and well, including the year and everything, you have a monotonic description. And that's tau. The way we construct our time and date measurements by the usual conventions, that's just like introducing this external tau parameter. But our time measurements are based on fundamental processes in some way. And that's what represented by phi.
Okay, but do you think, I mean, also along the comment by Carlo, I mean, the monotonic time parameter has to be associated with a certain irreversibility. And can you make a comment, or can you interpret the behavior, the decoherence behavior of your wave packet that you presented somehow somehow as an effect of such irreversibility, or not?
I don't think in this system the model is time reversible, time reflecting symmetric.
Mm-hmm.
Because it's not a many-body system, so there's
Mm-hmm.
Irreversibility. But it certainly would be interesting to combine this, try to extend it to many-body systems, and see if there's any additional implication on irreversibility.
Okay, so if we have no more questions, let's thank the speaker again.